see. Connecting. Good. Connected. Great. Looks like audio's working. I've got a capture of my webcam. Hey, Bumpley, good to see you today. It's interesting. The information on the chat log says that nobody's watching. That's okay. I know you can't make all of them, but it's good to see you. I'm a little bit behind today. Usually, I have the countdown going. I didn't get that up in time. Didn't get anything to share. Oh no! Well, thanks for joining us while you can. I really appreciate that. Let me fix some of this too. Okay. So I'm not sure I'm getting accurate information about who's here so far. There will be a part two. Today is just the introduction, and I'm not totally sure yet that it's going to be continuous, so I probably won't have Jitter part two as the next class. But um, you should definitely check out if you're into this. You should look at the last um, Learn with Me, where I was actually looking at a pretty involved Jitter patch by Timo Hoogland, which is still up on Twitch to watch. You should check that out. I think you'll like it a lot. But this is going to be much more focused and hopefully a little bit easier to follow along. So thanks for joining in. I think I'm gonna sort of do a gradual start today. Let other people have time to get started. What I've noticed is that it usually takes a few minutes after I initialize the stream to get people to actually catch wind that it's happening and make their way over here. So I'm just sort of caffeinating myself in the meantime. Okay. All right, so I guess I will go ahead and get started just to begin the discussion. Um, Discussing jitter, which is the world that we're going to dip our feet into today, is a tricky topic. It is this might be a little contentious, but I think it's fairly safe to say that generally speaking, uh, Twitter jitter tends to be more complex than MSP or standard Max for a number of reasons. Um, Primarily because we're working in two domains. We're working on the CPU and on the GPU, whereas normally we're just working on the CPU. And also because we're working with much more complex data sets than if we're working with something like audio, whereas audio tends to be sort of a two-dimensional stream of values. You have amplitude over time. When we're working with jitter, because we're working with video, we have what we're going to refer to as matrices, which are effectively grids of data that are multiple dimensions deep, and there's just a lot more information to process at any given moment in time. So doing a deep dive into jitter requires some really complex understanding of some involved topics. But I do think that I can provide a fairly comfortable starting point for people who want to understand the visual component of the language Max. So, like I said, when we're working with jitter, we're really talking about two different domains, the domain of processing on the CPU and processing on the GPU. When Jitter was young, there was no way to communicate in Max with your graphics card. And that was kind of a bummer for a long time because, well, the graphics card is an entirely separate processor designed specifically for rendering this type of data. And the graphics card processors can be incredibly powerful and can keep the rendering of video from providing too much of demands on the CPU, right? If the rendering can happen on the GPU, then the CPU is free to do whatever it needs to do. However, we didn't, again, to jump back to what I said a moment ago, we didn't have access to the GPU when Jitter was young. Everything was processed on the CPU, and it was very easy, and continues to be very easy if you're working on the CPU, to sort of overload the demands of your system relatively quickly. Like if you think about a CPU needing to process a multidimensional matrix that is particularly large and process that at 30 to 60 frames per second, you can really bring the CPU to a grinding halt as far as the amount that it can do pretty quickly. And what that means is that until we were able to access the GPU, it was very difficult to get high fidelity, high frame rate processes happening. And eventually, C74 dealt with this issue by incorporating OpenGL into its structures. And OpenGL is the open graphics processing language that a lot of different technology runs on. And OpenGL was a wonderful solution to this problem because it's incredibly scalable, it's incredibly flexible, it's incredibly powerful, and it does communicate directly with the graphics card. But it created this sort of division of labor in the Jitter world. On one side, you have traditional Jitter, and the traditional Jitter objects are going to be all the objects that we see with JIT dot something in their name. So the couple of Jitter objects that I'm using here are all the traditional Jitter objects. And then on the other end of the spectrum, we have the objects that access the graphics card through OpenGL. And those objects, mostly, with one important exception, use JIT.gl at the beginning. Right, so today we're going to see a lot of JIT dot objects, and we're also going to see a lot of JIT.gl objects. And I want to talk about first one, then the other. When we process stuff in the standard JIT dot, meaning we're working on the CPU, we're going to be thinking about what we call matrices. A jitter matrix is basically a bit of your RAM set aside to store and allow the CPU to process visual grids. Okay, so why do we think about grids? Well, that's the way that modern screens work. We have grids of pixels, and so if you were looking at the monitor that you're looking at right now as you're watching this, very likely it's at least what we call a 1080p display, if not a 4K display. If it's a 1080p display, what that means is that you have a grid of 1,920 pixels moving along one axis, the x-axis, and 1,080 pixels along the y-axis. And you multiply those two values together and you get the total number of pixels in that grid. But it's actually trickier than that because we have multiple layers of pixels for different colors. And we need to understand that those layers are, at least in the space of working with video in software, we have a red, a green, a blue, and an alpha layer. And that alpha layer will be transparency or brightness. I forget which one. But the important thing to remember is that we're working with a grid that has an X, a Y, and a Z-axis. And that Z-axis is going to be 4 layers, while the X and Y will be significantly larger. So it's a multidimensional grid. And the output will be a single flat image or a stream of frames of single flat images. And the matrices are where we're going to store these collections. Now, in the OpenGL world, what we have instead of matrices are entire three-dimensional contexts. And what we'll find is that we can place items into these contexts, and we can move items around these contexts. But we're moving from a dimension that is technically 3 dimensions, but it's really only 4 deep in that z dimension, to one that can be as deep and wide and far around as we want to within this 3-dimensional space, and then we're going to capture a snapshot of that to display as a flat image. So let's start with the easier one of those two, which is the jitter matrix world. Okay, so just like with audio, we have the ability to get sound out to our sound cards. With video, we want to be able to get our matrices, our grids of data out to a window that we can display on our screen. And that's what I have here in this starting patch that I kind of threw together. The jit.window object generates a window that you can then send a matrix to, or you can actually have it call up a matrix. And this window is flexible, and as you can see, this is not, by default, it's not retaining the aspect ratio of the initial screen. So I kind of have to make some assumptions here about that. And we have another option. If we want to continue to just work with matrices, we can do a jit.window and we can do a jit.p window. The difference is that the jit.p window will display in the patch. So that's a patch window. And they also scale. And we can send, just like I'm sending, I'll come to the jit.grab object in a moment. That's how I'm getting my webcam capture. But just like I can send this sort of, we can think of it for now as a video stream to the jit.window, I can send this to the jit.p window, and it will display there too. So even without going really into the details of what's going on here, we can see that right out of the gate, this sort of workflow is very similar to what we're used to Max workflows being, right? Objects do something and they send the output of what they've done onto something else. But it's actually not quite that simple, and the further we get into jitter, the further afield we're going to get from what we're sort of used to the Max workflow being. Right? And so why is it not that simple, right? Why is it not that we're sending the output of the jit.grab onto the P window or the window? So the way that we deal with data in jitter, again, is via this concept that we call the matrix, right? And the matrix is very similar to the sound world's buffer, right? So when we're working with sound, if we want to store data or store sound data, either something that we're recording in real time but we want to hold on to, or if we wanted to store, say, an audio file for playback, we would use a buffer. In jitter, we have the jit.matrix, and we can actually make a matrix, and it sort of acts identically to a buffer, except it's for video. It's a place on the hard drive where a video data is going to be stored so it can be processed and mutated. But whereas with a buffer, we only ever needed it when we had data that we wanted to access, and then once it was accessed, we had the audio stream moving from one object to another. In jitter, most objects actually retain their own internal matrix because we're dealing with so much data, and that data needs to be, processed in kind of careful ways. Usually what happens with a jitter object is it will receive access, or it will receive a pointer to one of these matrices that exists. Um, and then it will copy that matrix into its own internal matrix where it can make whatever changes it wants to. And that way it actually leaves the original matrix unaffected while it does its copying. And maybe what I can do to clarify this a little bit more is for a moment I'm going to turn this metronome off, and now my image has frozen, which I knew would happen, but that's sort of a funny way to freeze it. Let's just try freezing with a nice smile. Okay, so now I've frozen the image again. And instead of using this metro, I'm just going to place a button above the jit.grab. And I want to see the exact information that's coming out of the jit.grab object. Now, what's interesting is that I'm using we can see that the jitter objects have their own cable, their own patch cable, that are distinct from max objects and distinct from MSP objects. But we can actually we can hook the jitter output up to a message box. And look at what happens when I send a bang to the jit.grab. So one thing, it updated my screen. So I'm going to reset that again. There we go. And it output this message, JIT matrix, and then there's this long string. So the long string represents the location on your RAM, or on my RAM in this case, to where that matrix exists. And it sends just the name and the location of that matrix onto the next object. When the next object receives that name, it will make a copy of that matrix and store that copy in its own internal matrix for processing. That's usually what happens with jitter objects. Now, with the jit.window and the jit.p window, it doesn't need to make a copy, it just outputs. But it's not enough to simply tell it, hey, look at this matrix, because it actually needs that message to be reiterated every time we want it to look at that matrix again. The content inside that matrix is being updated by the object over time. So the jit.grab object looks at webcams. It looks for webcams, and it will store the output of the webcam in its internal matrix. And when I send the name of the matrix onto another object, the object will grab the matrix at that point in time. And then it can process it and do whatever it wants with that grab, that capture. So if I wanted to update the window, I would need to send additional bangs. And every time I do, it will store and display the matrix that was in the jit.grab at that point in time. And that's why we're using a metro in the first place, because the metro will bang at a reoccurring interval. And in this case, we're using a queue metro. The queue metro just makes sure that the bang itself goes into the low priority thread if the thread of things that needs to happen gets too long. It's a way of ensuring that the actual bang of the metro doesn't override or supersede priority of things that may be more important. So it's just a very simple variation on the metro object, and the normal metro object could work just as well. But this is sending out a bang every 30 milliseconds in this case, which is more than enough time for us to see this stream of individual shots as a continuous video feed, right? But really what it's doing is it's telling the jit.window and the jit.p window over and over and over and over again to grab and output what's in the matrix, the jit.grab at that moment. So, to finish going over this introduction to jitter, I'm going to clean up some of this. We don't need that display, and we don't need this anymore. Let me just quickly finish the introduction to jit.grab. That's a fun way of working with jitter, right? Working with your webcam. It's always exciting to see how you can like mess up your face, right? So jit.grab expects a 1 to access the first webcam that it sees, or a 0 to stop accessing it. It can also respond to an open or a close, which will work the same way. So if I hit open, it will open the webcam, which is already being accessed. If I hit close, it will stop it. So even though I'm still sending bangs to the jit.grab, it's no longer accessing my webcam, and so it's not displaying. So what I need is two things for the jit.grab to work, minimum two. I need one to say to access the webcam, either open or the value 1. And then once the webcam is being accessed and basically the feed of the webcam is being sent into the jit.grab matrix, we need to send a bang at regular intervals to the jit.grab to send that data on to other locations. So while we're talking about sources, even though I enjoy working with the webcam stream, it is worth noting that we can work with pre-recorded video files, and we can render video as well if we really wanted to. But for the sake of simplicity today, we're going to stick with the webcam. If you wanted to use video files, there is you can actually just drag and drop a video file from anywhere on your computer into the patching space. You can also drag and drop. You can access the video tab on the left, and this will show you these are the video files that Max can see, and my collection will be a little bit different from yours because I've added some different files over time, and you can see it's kind of lost some as well. But for example, I have this video file. I can drag it in. Oh, and I had the patcher locked. That was my mistake. We want it unlocked when we drag the video file in. And this generates a little shortcut video player, basically, using an object called jit.playlist. It's a really convenient object, but it does the same thing. Basically, when you hit play, it has its own jitter matrix where it's storing the video, and when you hit play, it will begin to output the individual screens in the matrix. So if I replace the jit.grab to jit.window, if I sent the file player to jit.window instead and hit play, it looks like it did not like. Let's see if I give that bangs. No, it looks like it's just not liking that video. So let me try a different video. I'll use this built-in one. Yeah, I can see that loaded better, so there must be some other issue going on there. So I'm going to connect it to this basketball and play that. I'll set loop on. So often, and you can actually hear, sounds like that outputted some audio too. So you can hear working with video files can be really easy. Working with webcams takes a little bit of setup. And this worked so conveniently for me because I have a single webcam. If you have multiple webcams, what you'll want to do is you'll want to grab the jit.grab from the help file, which is a little bit further extended, and it shows you a more complex setup where you can get a full list of webcam devices. And this won't work because I'm already streaming over here, so it's not going to display here. But you can actually get information about formats that your webcam expects, dimensions, etc. So there's more to the jit.grab object than what you're seeing here. It's a pretty versatile object. But for today, I just needed something to work with. Now, what I will show you is that there are a lot of ways to manipulate jitter objects, and you can actually do quite a bit on the CPU without ever going to OpenGL. But some of these do get pretty involved, and some of them are pretty easy. So I wanted to show you just some fun ones that are easy, some fun objects for simple video manipulation. So one object is jit.slide. And if we look at what this says, it says cell-wise temporal envelope follower. So that's a pretty confusing statement. If we look at the demo, right, in the help file, it says again that it's a cell-wise temporal envelope follower. And if we look at the way that this is set up in the demo, we can see the source, the video file I actually just played, going into the jit.slide, and then the output of that is connected to a P window. And then it has two control parameters for it, one that says slide up with a number box associated with it, and one that says slide down with a number box associated with it. And what I want to observe about this is that it's using these two objects are attrui objects. Those are the objects that show you the attributes and allow you to manipulate the attributes. Um, this is something that's pretty different about the way that jitter objects seem to work, generally speaking, compared to MSP objects or max objects, is that a lot of them expect the changes to be made not with standard messages, although there are standard messages that you can make, but often the biggest changes that you can make will be made by changing the attributes to the object. Those attributes are the things that typically we set either when we instantiate the object, or we may set by going into the inspector. Um, it's actually, we're going to want to access those attributes to make big changes. And so what we're going to see over and over and over again is that we will see lots of attrui objects paired with jitter objects as the sort of preferred way of controlling the way that those objects function. So I'm going to take the jit.slide and I'm going to connect it in between the jit.grab and the jit.window. And we can see by default, we're not really seeing a difference, right? But then I'm going to create an attrui object, which you just hit A on your keyboard, right? And then whatever you connect it to, it will then show you the attributes that you can change for it. So we've got slide up and slide down as the two sort of initial attrui elements, just so happens to be the same ones that we saw in the help file. And if I connect them slide up, slide down, now we have number boxes next to them that we can affect. And if I actually start to increase these values, what we see as I begin to move around is that this sort of introduces effectively a smearing effect. And so if you think about an envelope as something that opens up and then closes again, it's as if the pixels overlap and then disappear over time. And so the slide value will actually eventually determine the speed at which prior pixels begin to disappear. And so the jit.slide object is a really easy, really cool effect. So you can see that the P window over here, you have my original output, and then the jit.slide, you have the modified output. And of course, this gets more imposing the more we increase those numbers. There's one more thing I want to do, though. I'm going to go into the audio status window, and I want to show you CPU load. Now notice that the CPU load says 0%. You may take this to mean that this video manipulation is not really impacting my CPU, and that's not true, unfortunately. If I, just as a demonstration, decided to add a bunch more jit.slide objects, so I'm just going to keep adding these for a while. So I probably don't even need to hook them up, but I do want to hook them up just for the sake of demonstration. So let's go through 4 jit.slides. And then let's add in some more. Notice that the CPU continues not to change. It continues to display a value of 0. And at a certain point, my frame rate is going to drop, but the CPU load is still going to say 0. So the whole reason I'm pointing this out is because it's worth noting that while jitter does affect the CPU processing percent, the only CPU display that we can get in Max without some very, very tricky coding is the amount of CPU load that the audio engine is requiring. All right, so it's actually much more challenging to keep track of jitter's CPU load, which is unfortunate. I've always wished that there was a CPU display that captured everything that Max was doing. Maybe by the time Max 9 comes out, they'll have that. We can keep hoping. Okay. So Let's go back down just to one jit.slide. We don't need all these additional ones. We're almost at halftime, and I do want to switch to the OpenGL context and working on the graphics card. But before we do, I'll just show off one of these easy to use jitter objects because they do exist, and they can actually be really powerful, as you can see. Like just changing a couple of values makes a big impact here. So another one I want to show is jit.sprinkle. And again, by default, it doesn't look like it's doing much. It is kind of, but it's so subtle that it may be hard to understand exactly what it's doing. So let's go to the help file. And we can see that what this does is it introduces spatial noise. Jit.sprinkle probabilistically determines whether a matrix cell will be displaced by a random amount along the horizontal or vertical axes to produce a cloud of data surrounding the original data cells. So what does this mean? Well, first off, let me just really quickly state that when we're talking about data in the matrix, every location in the matrix is called a cell, right? So when they talk about matrix cells in this description, they're talking about individual locations. And so what this is going to do is it's going to create random displacement for each of these cells. In other words, cells may, using probabilities, be replaced or swapped with the values in nearby cells. And we see three attributes being used, being called up from the Attrui objects: probability, displacement probability, horizontal displacement, and vertical displacement. So if we try to replicate that here, let's make one more Attrui object, and let's do the same thing: probability, x range, and y range. So probability needs to be between 0 and 1, so it's not a huge range. And notice I can increase this all the way up to 1 and beyond, and it still is looking the same. That's because we need some other values to change first. So I'll set this to like 0.1, and then I will start to increase the x range and the y range. And we can see that we're starting to get these frames. It looks kind of like noise, right? And there's this sort of neat function where when the background is more or less a single color, the noise is less noticeable. It's there, but because there's so much consistency to the value and the pixels around there, it looks like it's not changing. But then we can see that like blocks or cells around this piece of wood are sort of randomly being displaced in this range around. Say if this is the original pixel, it might appear up here to down here. So we are displacing that. The greater the probability, the more likely these pixels are going to be displaced at any given frame. So one last thing I'll point out before we switch over to OpenGL, just to go back to that discussion of matrices and matrix copying. From the jit.grab, again, there's the sort of unique, it's almost like a GUID or almost like a randomly generated string. I'm sure it is a GUID, a randomly generated string of some kind. Notice that the name of the matrix coming out of the jit.grab and the name of the matrix coming out of the jit.sprinkle are different. And this is key to how jitter objects work differently from MSP objects and max objects. With an MSP object, a string of amplitude values, or a sequence of amplitude values, travels from one object to the next, and in that following object, those values are mutated, adjusted, however they need to be, and then those new mutated values get shared. With jitter, every time a new message is sent out, it's actually saying, hey, look, object over here, or object over here, I've got this matrix that I want you to capture, adjust, and do something to. And so it's actually saying, hey, find this matrix out on your RAM, make a copy of that matrix, and then you can share that copy. So the flow of data feels a little bit different, and that's why what we're getting out of the objects is just this message of JIT matrix. So I want to change gears, and I'm going to move this patch off the screen, but I'm going to leave the patch going. I'll increase that random probability so that I continue to seem be a little strange, a little unfocused. I'll bring this over here, and then I'll make a new patch so that we can talk about OpenGL in Max. So if we want to access the graphics card to do our processing, which often we do want because it gives us a ton more power, and the graphics card is an entire, expensive chunk of your system designed for thinking about and dealing with rendering of three-dimensional objects, we need to use the jit.gl library of Max objects. But the first thing that we want to do, similar to having a jit.window, but similar but different, is we want to create our three-dimensional space. We want to create the space that we're going to build in. And once we have the space, we can point a camera into it to capture a flat image to share in a window. Now that seems like it might be difficult, right? Okay, so first we got to figure out how to render a three-dimensional space. Then we have to figure out how to locate and place a camera within that space. And then we need to send that to a window to display that. And that is actually, historically speaking, in the before times, before the object I'm going to show you next, that's how that would be done. But now all of those processes have been wrapped up into a single object, simply called jit.world. So notice that it doesn't say jit.gl, but it is creating a 3D context being rendered in OpenGL on your graphics card, despite the fact that it doesn't say jit.gl.world. So jit.world does all of those things, and it has a variety of arguments that it can be given, or a variety of attributes that it can be given. But there's one argument that we can give it, and that's a name. We can name this unique three-dimensional space. The name can be whatever we want, but it has to be a unique name. In other words, we can't have two jit.worlds with the same name. And we are not required to give it a name, but it will be limited as to what it can do if we don't name it. So I'm going to go ahead and call this jit.world hello world. Now the name needs to be one word. Spaces, as I've discussed in previous classes, implies that we're done with one value and we're moving on to a new value. So I'm going to call this hello world, one word. And notice that this creates a window. That's because the jit.world is sort of an all-in-one. It renders the three-dimensional space, places a camera in it, and then sends that output to a window. But we don't have anything to look at in this world, and so it just looks like darkness. Now, if we want to, the one thing that we do need to do is we need to turn on or off the rendering of that 3D space. And that's really simple to do. All we have to do is toggle it on or off. And when I turn the toggle on, notice that the color goes from being black to being this sort of dark gray. It might not seem like a big change, but it's enough to allow us to understand that there's some sort of ambient light in this space, but we still don't have any objects in the space. Now, once we start working in OpenGL, a lot of the ways that we're used to working in Max get flipped on their head, and things simply aren't going to work as we may necessarily expect them. We need to learn some new ways of working with things. So the first object that I want to show you is actually a pair of objects, because what we're going to do is we're going to place a three-dimensional element in this space that we can play with, right? And a really simple starting point for this element might be a simple shape, like a cube or a sphere or a tetrahedron, some basic three-dimensional shape that we can play with. The way that I want to do this, it actually requires two objects. The first object is a mesh. So a mesh is basically a collection of interlocked polygons or triangles. And then once we have the mesh, we can use an object called grid shape to conform that mesh into the shape that we want. So if I do jit.gl.mesh, there are some really, really, really meaningful attributes we can set for this, but I'm just going to make the mesh now. And then jit.gl.grid what I can do, no, okay, so right away, as soon as I did that, notice that we got something on our screen. And that's really strange, right? Like nothing is connected here. So how are we getting anything? Well, typically when we add elements, add three-dimensional elements to our 3D rendered space in jit.world, if we don't provide a name for the space we want to send it to, in other words, this jit.world is called Hello World. There may be 4 other jit.worlds outputting their own windows. If we don't provide a name, it looks for the nearest jit.world it can find. And if there's one in the same patch, then that's the nearest one. And so it just gets a default placement. And sort of similarly, let's connect these together. Now we can connect these. But it did sort of the same thing with the mesh. The grid shape said I need to have a mesh to shape. And if I'm not connected to a mesh, I'm going to find the closest one to work with. So very, very strange, very different way of thinking about things, right? Like suddenly elements are communicating with each other without our connections, right? And even though we did that before with sends and receives, this didn't even require a corresponding name in order for it to work. Although we could have pointed it to a specific name. Now, there are some other presets that I recommend for the jit.gl grid shape and the jit.gl mesh. And instead of typing each one out, I'm just going to copy paste them from another screen in. So I'm going to delete those two. And then I'm going to copy paste. Again, it's the same thing, jit.gl grid shape to jit.gl mesh. And then I'm going to show you what these different attributes are. All right. So notice these have a lot of, after the name, an @ sign followed by a word and then a value. This is the traditional way of setting attributes for an object. We can also use the attrui objects, which we're going to. But this is setting the initial attributes. So both of these are depth enabled, meaning that they're not simply flat, but they're extended out to be 3-dimensional. Smooth shading will simply smooth out some of the less linear transitions. Lighting enabled is going to be awesome because we're going to see that we can add light sources to our scene, and that means that these objects will actually be affected by the light sources. The scale value on the grid shape scales it so that it's not filling up the entire space, but actually a little bit smaller. That's why the circle itself doesn't fill up the entire screen. Poly mode, I'm not so sure about what poly mode is, but we could look into that in the help file. So again, no name for the jit.world, right? They're just communicating with each other because it found, it's the nearest 3D space that it can find. Now I'll show you some cool things. If we go to the output window for the jit.world, we can click, well, we will be able to in a moment. I need to set up some more things, but we can actually rotate this object and see it in some different angles. So one of the problems with rotating this object is that it's a sphere. So it looks the same all the time. Maybe we should change this object from a sphere to something like a cube. So that is, like most values in jitter objects, an attribute. And if we're going to change an attribute, the easiest way to do it is with the attrui object. I'll hook the attrui object up to the grid shape, and we'll find shape. A lot of attributes for this, and we'll see that a lot of these jitter objects are very complex and have a lot of attributes, which is good. It means they're flexible, right? So there's a torus, there's a cylinder, there's a cube, but we're really close to that cube. We need to pull it back a bit. There's a cone and a capsule and even a plane, right? So pretty fun and flexible. Now we can change more values on this object as well. If we grab some more attrui objects and hook them up, we can see other things that are manipulatable, right? So let's check out what else we have. We can change the color of the object. All right, so when I selected color, it replaced the name with the actual name for that value, which is GL color. And then when I click on it, it brings up our window. We can play with the color. We can keep going, and it might be nice to reposition this. So let's go to position. With position, we have 3 values, X, Y, and Z. If I move the X value, we can see that we're moving this object to the left and to the right. Y is up and down, and then Z is forward and backwards in space, right? Let's keep going with more attrui things, see how else we can play with this. So we can rotate this object along the X, Y, and Z axes. So we can see this requires larger numbers. But there's X, Y, and Z rotation. All right. So we can see that if we can provide the proper messages, we can actually manipulate these values quite a bit. Now, I like sort of settling on the rotation, turning the object, and positioning the object, because I want to show you that there's an object that's actually designed to generate changing values over time, to generate animation to a 3-dimensional object. So we can do it manually like this, or we can use a jit.anim.drive object. So again, what this is going to do is we're going to give it some settings, and it's going to actually generate the messages to move the object that it's associated with. So we're going to associate it with the grid shape, our torus currently. And this can take different types of messages, and we want to be a little careful with this because the wrong message can send this far away. But you can see there are messages like move, turn, and grow. And the numbers that we have here correspond to the various axes. So you can see that we can actually generate some pretty cool things in this demo, but let's keep it pretty basic for today. Let's try the turn message. So turn 010. I'm just taking that message from the help file. I'll send that message to the jit.anim drive, and our donut torus is off to the races. Let's try turning that into a cube, cone, capsule. And if we look at what's coming out of that, notice the rotate XYZ is changing now. And there is the sort of message coming out of the anim drive that's affecting the jit.gl grid shape. So let's try changing this message from turn 010 to 011. Notice that now we're getting rotations across multiple axes. And if I increase the size of one of these numbers, let's try 020. And then let's crank that way up. So that number corresponds to the speed of the motion. So maybe we want it rotating really quickly along one axis and more slowly or slower along another axis. All right, so now we have rotation. And I'll turn that rotation speed down a bit so we can keep seeing that, but we can maybe make this a little more comfortable. Cool. So the last thing that I want to show off is adding a light source to a scene. You can add as many light sources as you want, as long as your CPU can handle it, and you can position them however you want it. Again, as long as you have the resources, not CPU, GPU. We're working on the GPU now. To add light source to a scene, we use an object called jit.gl.light. So this will place a light source onto a scene, but I have noticed it seems like this one works better if it actually has the name of the scene you want to send it to. And I believe, yes, that's just the argument. So we'll give it that argument saying that I want you to add light to the scene that we're rendering in the jit.world that we've called hello world. And we need some more Atrui objects. So I'm going to do another copy paste just to grab the Atrui objects that I want to work with. Actually, let's build it up together. So first, there's a simple enable toggle to turn the light on and off. It's defaulted on, but we haven't really set it up yet, so it doesn't look like much is happening. Then let's change the type. So there are actually different ways that the light can be displayed. It can be displayed as a directional light, a point. So there we can actually see that that changed the light in the scene, or a spotlight, meaning that it will. So the light can either point to a location, it can point sort of in a general direction, or it can be treated like a spotlight over the scene. Then let's try moving the position of the light. So we're going to do this with position, and with rotate. Okay, so let's try. I'm going to move this out a bit more so I can see it. So we've got the scene set to be a spotlight, and you can see that as I move the spotlight along the x-axis, it sort of moves to the right and to the left of the scene. So if we move it too far to the right, it no longer shines on our object. And along the x and y axis, we can see that we're moving that spotlight up and down. And then along the z axis, I need to do larger values. Again, bringing it further towards the camera or away from the camera. And a directional light will have a slightly different impact than a spotlight. Same with the point. Each of these methods for working with light will result in different outputs. So to sort of finish our play with jit.gl today, I'm actually going to show you just a really neat little patch that you can find in the help files for jit.gl mesh. And to get this working, I need to turn off this instance of the camera because we're going to load the camera up again in a different patch. So I'm going to close the patch that I built before, and I'm going to go into the help file for jit.gl mesh. Because since we're only scratching the surface today, I want to show you some cool things, just an example of a cool thing that can be done. So in this demo, we have the jit.world object, but this one has a different name. They've named it mesh CTX. And there's this really cool example of the grid shape going to the mesh, because this is sort of the most common example that you see with meshes is that they're being shaped by the grid shape object. But on the second tab of this demo, there's a demo of what they're calling point cloud. And I'm going to turn on the jit.grab. And now we've got my face sort of superimposed on the image over here, because again, these contexts are being rendered in the same three-dimensional space. And so it just so happens that like the placement on the z-axis of my face is sort of overlapping with this current one. And you know, if we look at this subpatcher, so what's happening is that the jitter image, the matrix, is being converted to what's called an OpenGL texture. So a texture is sort of the graphics card equivalent of the matrix on the CPU. And in this window over here, we are making some changes. Notice we're using a jit.gl grid shape here. So we're sort of combining matrix processing with OpenGL processing, but it's outputting a jitter matrix at the end of this this subpatch. And basically what the subpatch is doing is it's taking luminance data and converting that into data that's valuable to sort of understand the z-axis. So when there is a larger difference in luminance, which tends to happen at sort of the boundaries of objects, it's using that difference and pushing those darker elements further back on the z-axis, which creates a sense of three-dimensionality. So it's taking a flat image on a webcam and superimposing a sense of depth to it. So that matrix then is going into the GL mesh. And so instead of saying what we want to render is a three-dimensional object, or it is rendering a three-dimensional object, but the three-dimensional object is the image from the webcam with depth added to it based on luminance. And so if we check out the z displacement amount, the higher I make that z displacement, the more we get this sort of three-dimensionality or depth based on change in brightness. So you can see what's being done is that the image is being converted into a series of individual dots, or what they're referring to as the point cloud, right? And then those dots can be moved forward or backwards in space. And a fun thing that we can do here, so notice what the mesh is doing. The mesh is set to draw mode points, which means that instead of drawing vertices as triangles, it's drawing locations as points. We can actually change the size of these points, and the thicker the points, right, the more sort of cohesive this image begins to appear to be. And so the more displacement we have on the z-axis in combination with thicker or larger or smaller points, we can get this really cool three-dimensional effect where we're taking our face. I'm rotating the cube or the shape behind me. We're taking our face, the picture, the flat picture from the webcam, and converting it into a three-dimensional shape. So this is a really cool effect. You don't have to apply it to a webcam. You can apply it to any video, right? So if I were to unlock the patch, go to the video collection, grab our basketball video, and reroute these two cables. So, and then start that playback. We get that same sense of depth superimposed on this scene. So it's a really neat, flexible chunk of code. And it's fun to play with. All you have to do to make this chunk of code work on your patch is you take the objects that you want to work with. So I'm going to reconnect it the way I had it before, delete that. I'm going to take this big chunk of code. Don't save the help file. I'll bring that chunk into here. And the important thing about how this is working is the jit.gl mesh. Notice that it is actually pointed to a specific jit.world render. So if I wanted it to render on my patch, I'd want to replace the argument that is the jit.world name with the name that I've got, which is, in this case, hello world. So now it knows to point to that render. And I've got my rotating capsule along with the output of my face. So I hope that was an interesting and exciting introduction to the idea of rendering on the CPU, rendering flat images via a four-dimensional matrix, or I guess it's a, four-dimensional matrix, right? Or three-dimensional, X, Y, Z, with 4 planes. And rendering 3D worlds on the GPU, or three-dimensional spaces on the GPU, that we place items into, and then manipulate those items using various max objects. All right, I think that wraps up today's class. Thank you all for watching. I hope you enjoyed this introduction, and I hope it leads to a lot of really fun rabbit holes as you explore these new spaces on your own. If you have any questions, feel free to ask them. You can see this gets pretty surreal. And you're running through my EuroX so you can multitask. That's pretty cool. I think that's the first time I've been run through a EuroX, Spaceman. Thanks for the honor. I'll also point out before I call it quits for the day that there is the output of jit.world, because we can see that it does have some outlets. We can actually convert the output to a OpenGL texture, so we can say whatever's happening in here, render that down as a flat texture and send it on to some other OpenGL context. We can also output it as a matrix, which allows us to sort of go back into the world of the CPU rendering. But I want to open up the help file because there's this additional object that is often attached to the second outlet of the jit.world. And this additional object is called the jit.fps GUI. And what this does is it displays information on the current render. That's really useful. So I'm going to make a jit.fps GUI. I won't save that. Just do jit.fps GUI. And if I connect that to the second outlet of jit.world, we can get information that's actually quite relevant to us, right? Like I can see that this is rendering at about 60 frames per second, which is wonderful, right? But we can also see the millisecond interval for how often it's rendering. We can get the dimensions for the render. Well, okay, so that's not working here. Dimensions, plane, name. Some of these will only be applicable from other sources. But even just knowing the FPS is super helpful because we want to keep track of how hard we're pushing our system when we work. All right, everyone, I think that's my time for the day. So thank you all for joining me. I'll be back next week with more classes. So stay tuned, and happy patching, everybody. Bye, y'all.